Now, first you learn how to traverse a data structure, and then you learn how to insert something in the data structure. So I want to insert a new value. Let's say every node just contains integers. So let's say I wish to insert a new value 11. So I think just this much is not enough. This is a vague statement. Yes or no? I'm saying I want to insert something. Are you able to understand it completely? When I say insert something, what does it mean? Because I have not told you where do I want to insert it. I might want to insert it at position 1, position 2, or at the end. It's totally up to me to do that. Okay, can somebody tell me if there is a linear array containing 1, 10, 2, 5, 7, and I have to insert something over here in a linear array. What is the worst time complexity of insertion in a linear array? It is order n. Can you tell me when does it happen? I mean, for which position the worst case comes? Does it come whenever I have to insert it at the last position? No. Inserting at the last position is order 1, yes or no? Inserting at the last position is order 1, but inserting at front will have to shift all the elements 1 unit to its right. So that will take me order n time. Now let's talk about linked list. So let's say I have this linked list with me 1, 2, 3, 4 and 5, and I always have access to my head. So see, this head is just like every data structure has a unique identifier. What was the unique identifier of a stack? It was top, right? Similarly for queues, it was front and rear. Similarly for linked list, it is head. Okay. So if I have to insert something in the linked list, what will be the worst time complexity? No matter what position I am inserting it at, what will be the worst time complexity for insertion in the linked list? Okay, all of you feel it will be order 1. Do you really feel it will be order 1? What if I have to insert in the end? If I have to insert it in the end, I have to go all the way till here, and then only I can create a new node over here and then link that newly created node to this. If you are keeping a tail pointer, then also there will be a problem, because let's say you have a tail pointer and you want to insert over here, which is not at nth position but n minus 1th position or n minus 3rd position, then what will you do? So in the worst case, you will have to go all the way till the end. So the worst case of this was happening at the front, but the worst case of this is happening at the end. So that is a very, very important point to understand. So let's say the insert function that you have for your linked list is written in this way: insert a value at a position x, and just insert it. So it will be a void method. You're not supposed to return anything. You're just supposed to modify this linked list by inserting a new node containing a value val. Okay. So let's say I call this for 7 and my position x is equal to 3. So, or let's say 4. I want to insert it at 4th position. So I am numbering my position starting from 1. So this is my position 1, position 2, position 3, position 4. So if you have to, let's say, insert a new node called 7 over here at this position, then it is as good as saying that, hey, I want to create a new node 7 and link this to this and then link this to this. This is as good as doing this thing. Now there are few very, very important things over here. First important thing is that, let's say you have performed a new memory allocation. Let's say you have done that. This is pointing to this, and you performed a new memory allocation and 7 is present over there. Will you directly want to change this thing to point to this? No, because if you do that, then won't you forget the address of this? So what you should do is, before delinking any node, and this is rule of thumb in linked list, before delinking any node, you store the address of that in a temp variable and then make this point to the newly created node, and then make the newly created node point to that temp. This is the first point. Second point is, if let's say, so this was the case. If let's say I have to insert a new value at position 4, then you would want to start your traversal from here. Would you want to reach at 4th position, or would you want to reach at the parent of 4th position? You want to reach at the parent of 4th position, because You cannot, if let's say you have reached here, there is no way you can create a new node and link that to its parent. So if you have to insert something at xth position, you have to reach till x minus 1th position. I repeat it, if you have to insert something at xth position, you have to reach at x minus 1th position. So this is a very, very important point with respect to insertion. Okay, tell me one more thing over here. How many hops will be there? By hops I mean how many times this statement will execute. Let's say your temp is equal to head and you are going to do t equals to t next. So how many times this expression will be executed if you have to insert at xth position? Will it execute for x times, x minus 1 times, or how many times? Yes, it will be x minus 2. It will definitely be x minus 2. Because if you have to reach, what did I say? For insertion at x, you need to reach x minus 1. And to reach x minus 1, x minus 2 hops are sufficient. Because if you have to reach first node, you need 0 hops. For second node, you need 1 hop. For third node, you need 2 hop. Similarly, for x minus 1th node, you will need x minus 1, which is x minus 2 hops. So guys, these are very small things. You can do it by observation also, but they are pretty standard. That's the reason I am talking about them. Okay. Now there is one very interesting thing with respect to insertion in linked list. There is one edge case over here. So see, the easiest thing is that you always go to x minus 1th position, do a malloc, store this in a temp, link it to new node, and link new node to the temp. Right? This is the easiest thing that you can do. But my question is, there can be an edge case also with respect to insertion. Can somebody talk about that edge case? Yes. Insertion at the first place. If let's say somebody wants to insert at location 1 a value called 7, then I would want to create this 7 and directly link this to this. So there will be no hops for that. I just link this to this. But here, would you not want to change your head? Yes, that is the most important thing. So insertion has an edge case when the desired position is head. In that case, do not forget changing your head. And I have seen there are certain complicated questions on linked list also where you modify your head, and I have seen people forgetting the process of changing the value of head. So please do not forget that. Whenever head is getting tampered, you have to change the head. Otherwise, you will be in trouble. Similarly, I think I can talk with respect to deletion also. So let's say I want to delete at a position x. So let's say if I wish to delete at position 4, so 1, 2, 3, 4, I want to delete this node. To delete this node, where do you want to reach? Do you want to reach at 3 or do you want to reach at 2? So to delete a node also, you have to reach at its parent, right? You have to reach at its parent. And how do you delete a node? In order to delete a node, if let's say this pointer is p, you can simply do, you have to basically change this pointer to now point to this. And can I do that? Yes, I can simply write p next should now be equals to p next next. Now there are two choices. So now if you take a look at this linked list, while traversing it, I am never going to touch this 3. Although this 3 exists, but I am never going to touch this 3. So there is an optional step that you can take, and that is a good step to take. You can remove this node permanently, and there is a keyword to do that, delete, and to this delete you have to pass the address of this. So if you pass the address of this to this delete method, it will be deleted forever. However, that is an optional step, but that is good because it frees. There is another keyword also called free. Please explore these two, delete and free. So you can use delete or free keyword to get rid of the unwanted memory location. So now you guys can traverse a linked list, you can insert something anywhere, and you can delete anything from anywhere. Now let us take a scenario. Let's say you are manipulating with pointers. Okay, you are changing your pointers, and let's say you are doing sometimes you are doing p next or you are doing p data. Can you tell me what will happen if this p is null? If this p is null, then what will happen? So this will give you a kind of very well known exception called as null pointer exception. This exception actually comes a lot in industries also, in companies also. So your interviewer will be really worried if he sees that your code can give a null pointer exception. So your code must always be null safe. Whenever you are dealing with pointers, it must always be null safe. Null safety means that, see, wherever this arrow operator is going to come, the initial part of that must never be null. Must never be null. Okay, let me write an expression like this: p next. Okay, so null pointer exception here can happen at this level also if my p was null. If my p was null, the null pointer exception will happen here itself. But answer me one thing: if it is guaranteed that p is not equals to null, if this thing is guaranteed, then is this also guaranteed that this thing will never give me null pointer exception? No, because what if p next is null? P next can be null. See, here this p is not null, but p next is null. And if this is null, then still the null pointer exception can be given. So before doing anything like this, you must perform a check of this kind, that p not equals to null and p next not equals to null. You must have this check. If you do not have this check, then there will be trouble. Okay, tell me one thing. Is it sufficient to just have this much of check if p next not equals to null? It is still not sufficient. Why it is not sufficient? What if p itself was null? If p itself was null, then here itself you will get null pointer exception, which is in your if check only you will get the null pointer exception. Yeah, so these are again small things. Just write them somewhere or remember them, but do not commit these errors. Okay.